Hello, in this video, we are going to work with the remainder theorem, or the estimation of the remainder, with Taylor polynomials. So first, for the first part of this problem, we want to find the third term Taylor polynomial for f of x at being e to the x centered at a. So the third term Taylor polynomial is p sub 3 of x, and that is going to be equal to the value divided by 0 factorial x minus a to the 0. But as we know, this is 1 and this is 1. So I'm going to drop those both. Plus the first derivative at a over 1 factorial. 1 factorial is 1. Dividing by 1 doesn't do anything. X minus a to the first. Plus the second derivative at a over 2 factorial. X minus a squared. Plus the third derivative at a over 3 factorial. X minus a cubed. Using our table to find these derivatives, and find the derivatives at the center 0, our regular function is e to the x, and e to the 0 is 1. Our first derivative of e to the x is e to the x, and e to the 0 is 1. The second derivative of e to the x is e to the x, and e to the 0 is 1. And the third derivative is e to the x, and e to the 0 is 1. And we could keep going. We could actually, with this, find the power series, but we just need the Taylor polynomial. So all of these functions and the derivatives are all 1, and a is 0. So I'm going to underline that in a different color. All those a's are 0, and all the functions are 1. So the approximation is going to be 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Or 1 plus x plus 1/2 x plus 1/6 x cubed. There is our approximation with this third degree Taylor polynomial. We want to use the remainder term to find a bound on the error in the approximation on the interval 0 to 0.7. So we know that the remainder term is going to be less than or equal to m times the absolute value of x minus a to the n plus 1 all over n plus 1 factorial. We have the third degree Taylor polynomial, so we're looking for the third remainder. So the third remainder of x is less than or equal to m times the absolute value of x minus 0, a is still 0, to the 3 plus 1, which is 4, all over 3 plus 1 factorial. M is the largest absolute value of the n plus 1 derivative. And we are looking at the third Taylor polynomial, meaning the n plus 1 derivative is the fourth derivative. what is the fourth derivative of e to the x? Well, we know the third derivative is e to the x, so the fourth derivative is still e to the x. So we are going to look at the function of e to the x. And we're being told we want the error in the approximation on the interval 0 to 0.7. So we want this interval from 0 to 0.7. M is the largest value on this interval. Well, e to the x is an increasing function, e to the x referring to our fourth derivative. So the largest value of the fourth derivative between 0 to 0.7 occurs at 0.7. So m equals e to the 0.7. Because that's where this function is the largest. Meaning our third remainder is less than or equal to e to the 0.7 absolute value of x to the fourth all over 4 factorial. Right now we have generally a function that the remainder is going to be less than. Would really like to have a number. So what I can do is for x, I can plug in the number that on this interval will make x the largest, or x to the fourth the largest. And the number that makes x the largest is going to be 0.7. It's the thing that is farthest from the center of 0. So this is going to be less than or equal to, for whatever x on my interval I plug in, it's going to be less than or equal to e to the 0.7, 0.7 to the fourth over 4 factorial. Now, having this answer is great, would be as far as you would be expected to simplify this on any assignment, but giving some context to this number, e to the 0.7, 0.7 to the fourth, this is approximately 0.020146. So pretty small. Between 0 and 0.7, when I graph this cubic function, and I graph e to the x on the same window. So if I were to graph e to the x and look at the window between 0 to 0.7, and I were to graph the polynomial here, on this window, the polynomial is not going to be exactly the same, but on this window, the difference between the function and the polynomial is never going to be bigger than 0.020146. So the function and the Taylor polynomial are going to be really close together. We're going to look at some more examples of using this remainder term in the next 2 videos.